I roughly try to split this up half and half. We'll see how we go and where we take a break. So let's try to take a break somewhere around halfway as we go through this. So starting out with linear factor models, these are asset pricing models, which are really models for expected returns, which is how we think about pricing assets. An asset is a set of cash flows that we need to discount at an appropriate rate, and the central fundamental question of asset pricing is what is the rate at which we discount assets. Most asset pricing models that we have can be written in a linear factor representation, as the one that I've written out. Let me see if I can figure this out. Where I'm sorry, I saw Sydney use this yesterday, so this must work. Expected excess returns here. So that's the expectation of our return vector R minus the risk-free rate. Should be linear in a factor in the product of a set of factor loadings. I'm going to highlight right now that I'm going to carry through for the rest of this talk. Everything I'm going to do initially is unconditional. So there's no time t subscripts on the expectations, whereas, of course, if this was an outcome of an optimization problem of some agent, everything would be conditional in some time t information set. And I'll come back to that issue in a little while. And I'm even further going to simplify things in just a minute by looking at single factor models only, where I'm going to reduce the dimensionality of the factors from potentially many factors to only one. I'll come back to that issue as well. So the two most prominent examples of linear factor models are, of course, the Kappa asset pricing model. In the Kappa asset pricing model, the expected excess return on n risky assets indexed by I here are proportional to the assets beta IM, with respect to the market portfolio, times the expected excess return on the market portfolio, where the betas are regression coefficients, literally covariances over variances. And that comes right out of individual expected utility maximization problems, plus some assumptions on aggregations you would derive the CAPM. And most, that would be sort of the standard theory where you would teach an undergraduate or an MBA student. Alternatively, the other prominent example that I think of is the consumption CAPM. In the consumption CAPM, the underlying factor turns out to be consumption growth rates. And you can write down an approximate, at least, linear factor representation of that model as well, where expected excess return on our n assets, indexed by I here, are proportional to or equal to the betas of the assets with respect to consumption growth. So think of running a regression of our individual asset returns on consumption growth rates, multiplied by a lambda. In this case, the lambda has a structural interpretation, and it's equal to the agent's relative risk aversion coefficient gamma, multiplied by the variance of consumption growth rate through time. There's a reason why I put up these two examples, because they have a fundamental difference that guides us in terms of how to think about estimating and testing asset pricing models. In the first model, the consumption asset pricing model, the factor is an excess return, which itself is one of the assets that needs to be priced by the model. That is an extra testable implication that allows us to use time series techniques to estimate and test this model. In the second model, the consumption CAPM, the same is not true. The factor is an underlying macroeconomic factor that has no direct tie to the asset pricing model, back to the asset pricing model. And therefore, we're lacking one testable restriction. And it turns out that means time series techniques will not work. And we instead will rely on cross-sectional techniques to estimate that model. So given the popularity of these models, and as I said, you don't necessarily even have to start with a linear factor model. Oftentimes you might have a highly nonlinear model, but then decide to linearize it and end up with a linear model anyway, or a linear approximation. There's a humongous literature on how to test and estimate such models. And I classify them as into essentially two sets. There are time series regression tests, where the goal is to estimate the betas and to test whether the intercepts of our regressions are jointly zero. And we'll elaborate on that idea. And there are cross-sectional regression tests, where the test is to regress excess returns on estimated factor exposures, and then to test jointly whether the residuals are 0. And that, to anybody who comes from classical econometrics, is a really bizarre concept, and we'll elaborate on that idea as well. It actually turns out to be still a well-specified problem in this context. So the aim of the first part of this lecture is simply to survey these two approaches, put some perspective on them, link them up together, and see where and when and how they're different and when they're the same, and draw some general conclusions. All right, so first the time series approach. So first of all, let me just simplify notation here and stick with one factor. Everything here generalizes wherever you see products. You're going to start seeing, vector dot products and things. But there's nothing unique to a single factor setting in terms of the econometrics here. So when we have a model in which the factor is itself an asset return, a excess return on a portfolio of assets, such as it is in the case of the CAPM, for example, where the factor is the market portfolio, then the model applies to the factor itself, which means that since the factor has a beta of 1 against itself, the factor risk premium, the lambda term that we saw earlier in our regression, is identified by the expected return on that factor. That turns out to eliminate one degree of freedom from the model and produce a set of testable implications of the model, which says that I can write a asset pricing model as a time series regression of excess returns on my I assets, on factor returns on the market portfolio. And if it is true that expected excess returns should be equal to betas times lambda, it must mean that the alpha i's, the intercepts of this regression, are equal to 0. It should be equal to 0 univariately, which is how Black, Jensen, and Schultz first tested the CAPM. And of course, we'll get to next, they should be equal to 0 jointly as a set. So if I wanted to test whether or not the model applies to a single asset alpha I would simply use a standard t-test in a single time series regression of excess returns on factor returns. The key here again is that the factor has to be an excess return. If the factor is not an excess return, this equation doesn't hold. And moreover, there is no restriction on the intercept alpha I in this time series regression here. And the easiest way to see that logically is that we could have a factor that has a mean of 0. In fact, many of our fundamental factor pricing models where the factors are macro fundamentals or something other than returns, we standardize the factors in the first stage so that they're mean 0. That means that in this time series regression here, it would be the intercepts, the alphas in this notation, that would absorb all of the expected return from each of the assets, because the term beta IF would have a 0 mean due to standardization. So the critical point here is that when the factor is an excess return, we can think of the model as a time series regression and the model's testable implication as a test on these alpha I intercepts. So of course, you gain power by looking at a large cross-section of assets. So we would want to test whether jointly in a cross-section the intercepts are equal to 0. And the most straightforward way of testing such a joint test would be a Wald statistic. In the Wald statistic, you form a quadratic form of your estimated alphas and your variance covariance matrix of the estimated alphas, and that under asymptotic normality should be chi-squared n for n assets. And of course, the key to forming such a statistic is to evaluate what is the variance of the estimated alpha coefficients. Well, to do that, we need a little bit more distributional assumptions here. And typically, the way we proceed, at least in an initial stage of an investigation, would be to assume IID-ness of the residuals. So the residuals are independent identically distributed through time, in which case standard OLS results apply. That means that the variance of our OLS estimates are just x prime x inverse sigma squared. Well, here's the x prime x inverse. I believe we're missing an inverse right here. And so we pull out the 1, 1 element of x prime x inverse. And that turns out to be this expression right here. There's something that's interesting about this expression that we'll come back to in just 1 second, and that is that this ratio of expected return on the factor or volatility of the factor is something that appears over and over again in the statistical properties of linear factor model tests. This ratio right here has the economic interpretation of being the Sharpe ratio on the factor, the excess return on the factor divided by its volatility, which we call the Sharpe ratio. We'll come back to that in just 1 second. Now, if you wanted to make further distribution assumptions, in particular, if you wanted to, in addition, assume that the residuals are multivariate normal, then Gibbons, Ross, and Schenken actually derived a finite sample distribution for this Wald statistic, which is essentially just taking the original Wald statistic that we had, which is this term circled, and scaling it by an adjustment. On a multivariate normality, that turns out to be an F distribution. That is the Gibbons, Ross, and Schenken test. Now, in my mind, the benefit or the contribution of the Gibbons, Ross, Schenken test, however, is not necessarily the finite sample distribution part of the paper, but rather the interpretation of the Wald statistic. What Gibbons, Ross, and Schenken showed is that you can rewrite this statistic in this following form as a difference between two squared Sharpe ratios. This term over here is the squared Sharpe ratio of our factor, being the market portfolio. This term over here is the squared Sharpe ratio of the ex post optimal, mean variance optimal portfolio. And so what Gibbons, Ross, Schenken showed was that a Wald statistic on the intercept, a test of whether jointly all the intercepts in n time series regressions are 0, in the context of a Kappa, is equivalent to testing whether the Sharpe ratio, the expected return to variance trade-off, of our ex post best portfolio we can form in our assets is statistically different from the Sharpe ratio of the factor portfolio, which is the market in this case. So that gives us a sense for how some people like to think about joint intercept tests, and other people like to think about Sharpe ratios produced by portfolio sorts, for example. The two are intimately linked. And when I test whether or not jointly intercepts are 0, I equivalently test whether or not I can form a high Sharpe ratio by forming a ex post optimal portfolio. Okay, so what's the intuition here? This guy, the market portfolio, the factor, it is the ex ante mean variance efficient portfolio. It should be the best that you can do in terms of mean volatility trade-off. Of course, in any finite sample, you'll always be able to do better simply because you measure expected returns and volatility with noise, and even under the model. And so therefore you can do better, and the question is the amount by which you can do better within the statistical noise of the data? And Gibbons, Ross, and Schenken answers that question and shows that that is equivalent to a Wald statistic for the intercept coefficients alphas. So if I can flip you back kind of like a movie and just give you a sense of what we did. So we started out with a Wald statistic, and then we said, okay, well, let's add IID-ness, and we get under IID-ness we get an asymptotic result, the chi-squared n, with a covariance matrix we can figure out. We then add multivariate normality, we get an F statistic. But there's many cases when you don't want to make any of those assumptions, either IID-ness or multivariate normality, in which case McKinley and Richardson showed us how to estimate or test that Wald statistic in a general method of moments framework. And typically this is where I will stop throughout the lecture. You'll see me write down a set of moments, and then we know, standard GMM methodology applies, which means we have estimators for the spectral density matrix. We know how to do chi-square tests and so forth. But let me just walk you through a little bit of the detail in this particular example, since this is the first time that we together at least have seen GMM estimates. So GMM estimates are based on sample moment conditions. In this case, the sample moment conditions are just the normal equations of the OLS problem. OLS says the mean of the residuals should be 0, and the residual should be orthogonal to the regressor. That is the moment conditions in this GMM problem. The first one says the residual should be 0. The second one says the residual should be orthogonal to a regressor, which is the market portfolio factor, or the factor in this case. My notation here follows Cochrane, so this is an estimator of the expectation. It's just the sample average of CAP-T observations. So that's the same as test of asking whether or setting the residuals equal to 0 on average and making the residuals orthogonal to the factor returns. So if I find an estimator, alpha and beta, that satisfy these two equations, which I will be able to do because what I have here is a exactly identified set of two equations and two unknowns, I get OLS estimates because these are the first order conditions of the OLS problem. But what I gain is a general expression for what is the variance-covariance matrix of my estimates, which collapses to OLS results if my residuals are IID, but in general will capture conditional heteroscedasticity and dependence in the residuals. And the degree to, the extent to which you're successful at doing so, capturing heteroscedasticity and dependence, depends on your way of estimating the spectral density matrix. And that's another 3-hour lecture in and of itself, so let's not go there. But we got lots and lots of theory on how to best estimate a spectral density matrix in a standard GMM problem such as this. And this is even simpler because we got two simple moments and two coefficients. What happened? All right. So that was linear factor models. Do I have I just want to see where I am on time. Okay. So that's linear factor models. The unique thing, again, about being able to work with linear factor models, sorry, that was the time series approach. The unique thing of being able to work in a time series approach is that our factors are excess returns. Now, there are many cases in which our factors are not excess returns. And in those cases, we have to resort to cross-sectional regressions for testing the model. So when the factor is not an excess return, then it must not be priced by the model. That means we're effectively losing one restriction or adding 1 degree of freedom to our tests. So instead, one has to test the model cross-sectionally, and we do that in 2 steps. In the first step, what we do is we measure acid by acid betas, which we call factor exposures of factor I on our common factors. And we do that through time series regressions because that's the only way that we can identify exposures, because these exposures are by theory meant to be covariances over variances, OLS slopes. So we run a time series regression of excess returns of each of our acids on our factors, and we measure beta i's. And notice this is not alpha, this is A, an intercept, and that intercept has no theoretical restriction, as we already discussed, because the factor in this case is not an excess return. Equipped with a cross-section of beta i's, we can then run a cross-sectional regression relating the average return of our n acids to the measured betas of the n acids. That cross-sectional regression, where the betas are regressors now, should have a slope coefficient that's equal to the factor risk premium lambda, and the residuals here are alphas, because they're the differences between average realized returns and theory implied returns, which are lambda times betas. So let's ignore for now the important fact that we're measuring these betas here with error. All right, we'll come back to that. So let's just pretend that in our first stage regression, we get a perfect estimate of beta. Then it should be clear that the model implies a cross-sectional relationship between average excess returns and those perfectly measured betas. And that cross-sectional relationship we ought to be able to capture through a regression, the coefficient of which ought to be lambda. So if we run this regression without an intercept, which is not necessary, but the model implies a 0 intercept, so let's impose it. The OLS coefficients are very straightforward. We run across sectional regressions. The betas are now our x's, our regressors. So this is x prime x inverse x prime y. And then the alphas are nothing more than the residuals of this regression. They're just the differences between the data and the fitted expectation of the data that gives us alpha forecasts. And now we do the same thing as before. We just form a walled statistic. And the walled statistic is you form a quadratic form of your estimated alphas, and there's variance-covariance matrix here, and you get asymptotically a chi-squared distribution. And it all boils down to what's the variance of the thing that you're forming the quadratic form over. Except there's some caveats here. This is a bizarre problem, because what we're testing here is whether or not the intercept, I'm trying to go back, I'm sorry. Whether or not the residuals of a regression are zero. They are by construction in the cross-section. So we actually can't test that restriction. That's a silly restriction to test given the regression framework. So instead what we're trying to test is whether or not the magnitude of these residuals is surprising given the model. Now it turns out that in the standard OLS problem, if we didn't know about this first stage regression here, and we just took a regression of some exogenously given betas on some average returns, this regression here would have absolutely no implications on what is the magnitude of the alphas. It is simply just, whatever it is, it would reflect the noise in the data. But it turns out that in this particular example, due to the two-stage nature of it, the alphas, the residuals of the cross-sectional regression, are actually linked to the time series properties of the returns, and therefore we have a testable restriction here. The variance-covariance matrix of the residuals is, this beta x prime x inverse x term here, times the variance-covariance matrix of the underlying epsilons, and it turns out that this we can pin down from the time series regressions in this case. So that introduces a couple of complications in this test. First of all, this variance-covariance matrix here is singular, because there's an adding up condition that OLS imposes on our residuals in the cross-sectional regression. And so this is a generalized inverse, not a real inverse, in this simple way of writing down the problem. That's why this chi-squared statistic here, the same wall test we saw before, now has one less degree of freedom. That's because we removed one degree of freedom due to that adding up constraint. And then finally, as I mentioned already, what makes this all possible is the fact that we have information about the magnitude of the epsilons from the time series regression. That allows us to then test whether or not the magnitude of the alphas in the cross-sectional regression is too large given the model. So we're running this regression here. Initially, we assumed that these coefficients here, these alphas here, are uncorrelated. But very likely, if you think about the problem that we're estimating and the alternatives that we are considering, it is very likely that, in fact, these alphas here are correlated. And so if that's the case, then really the prescription from standard econometrics is to run a GLS regression and not an OLS regression. GLS regressions just look very similar, except we're weighting the x's with variance-covariance matrices. The x's are betas in this case. So now we're weighting the betas with the variance-covariance matrix of the underlying epsilons, and we get GLS estimates instead of OLS estimates. We get a GLS variance-covariance matrix, which we can show, as we should, is strictly smaller than what we get. I'm sorry. I keep getting flipped back and forth with the up and the down. Is strictly smaller than what we got from OLS. That's to be expected. We're using the data more efficiently. We're putting more weight on more precisely measured betas. We're putting less weight on less precisely measured betas. It makes sense that we would do so. Okay, so that's two-stage regressions in an ideal world where the betas that we're regressing our average returns on are measured perfectly. Of course, that's not true. The betas are measured with error. And so Schenken 92 was one of the first to formalize that problem and to derive an adjustment for the fact that the betas are actually generated regressors. His adjustment is very simple. It is simply a multiplicative scaling of the OLS and GLS variances of our estimates. So we're scaling by 1 plus, here it is again, the Sharpe ratio of our factor squared, both the OLS standard error or the GLS standard error. So what's nice about this magnitude here is it's not some cryptic formula of a bunch of unknowns or known quantities, but it's actually something of economic value, is that we can very quickly determine whether or not the Schenken adjustment has bite or doesn't have bite in a given application. Because it depends on the properties of the data, and in particular on what factor we're looking at and what is the sample frequency at which we're estimating things. So for example, if I were to estimate a Kappa cross-sectionally, and I was using annual data in my calculation, then I know that the squared Sharpe ratio of my factor is the squared Sharpe ratio of the market portfolio is roughly 6% risk premium over 15% volatility, or 16% adjustment. So that's the magnitude of my Schenken adjustment in annual data in the Kappa setting. And so quick back of the envelope calculations will help me understand whether or not that adjustment actually is important or not important in drawing inferences. If, on the other hand, I did this with daily data, my Schenken adjustment here would be the order of 252 smaller, and this number here would be really, really close to 1. Because, of course, I would have a lot more precision on my estimates. Now, the Schenken adjustment can be automated through a GMM framework. And that's kind of a logic that goes through all of my slides, and if you read Cochrane, goes through all of Cochrane, and it makes sense that that would happen. It's simply a historical development of techniques. We come up with a simple solution, we identify a problem and we fix it, and then we ultimately discover that all of it could have been fixed if we just framed it all in a more general estimation framework. And so here we go. This is the Schenken correction in GMM, and along with it, we get to relax a whole bunch of assumptions, as we always can in a GMM framework, non-IIDness of the residuals in particular. So here are the GMM moments for running a cross-sectional test of a Kappa. This looks very, the first two equations, first two sets of equations really, are just our time series regressions. Again, these are the normal equations from time series regressions. The first one says the residuals of my time series regression should be 0. The second one says my time series regression residuals should be orthogonal to my regressor. The third set of equations is the cross-sectional part. This is the equations that link returns cross-sectionally to beta, with the cross-sectional coefficient here being lambda. There's n of these equations in my system. I've added n cross-sectional equations. This is now an over-identified system of equations, just like it was, not unlike our time series setup. The betas are exactly identified from these two equations, but then this last set of equations is over-identifying the lambda. So what do we do when we over-identify a coefficient? Well, we need to weight the moments and collapse the dimensionality of the problem. And so here, there's two logical ways of weighting the last set of these n moment conditions that identify the lambda. If we weight the moments by our regression coefficients themselves, then what we end up with is the normal equations of a cross-sectional regression problem. So the normal equations of a cross-sectional regression problem are just like the normal equations of the time series regressions, are that the intercepts are 0, that the residuals are 0, and that the residuals are orthogonal to the regressor. Well, these are the residuals. If the residuals are orthogonal to the regressor, which we can enforce by weighting those moments by beta, what we get is OLS regressions. So by by weighting these two sets of moments with the identity matrix, and this last set of moments with a beta vector, we get OLS coefficients. And we get, as a result, then all the inferences that we would derive. We can use all the inference machinery from GMM in that context. If, on the other hand, we take this last set of moments here, and we instead weight them by beta times the variance-covariance matrix inverse, we get GLS. Because it would then correspond to the normal equations of the GLS problem, that the residuals are orthogonal to this particular combination of the beta coefficients. So both OLS and GLS are nested in a GMM setup of cross-sectional regressions. And the beauty of it is we get an automatic Schenken correction because there is no first stage, second stage estimation in this context. And we get to do this for non-IID residuals, so we don't have to make as strong a distributional assumptions on the problem. Everything else then becomes standard GMM. So it's a third, another variant of cross-sectional regressions that I want to highlight, and then we're going to come to some pictures that actually are going to illustrate the similarities and the differences between the three. And the third one is to rewrite the model in stochastic discount factor form, and then to estimate it with cross-sectional regressions, again, except in the regressor will be slightly different than what we saw. It won't be a beta anymore. It will be a expectation of the product of returns and factors. You'll see that in a second. So what's a stochastic discount factor? Stochastic discount factor is a random variable m such that the expectation of m times excess returns is 0. And what we can do is we can rewrite our linear factor models as linear stochastic discount factor models. I'll convince you of that in a second. So this is a linear stochastic discount factor model with actually already a normalization imposed. It's not a plus b times factors, but the intercept, has already been normalized. That's because the mean of the stochastic discount factor cannot be identified from excess returns. We would need to have a risk-free rate in this equation in order to identify the mean of the stochastic discount factor, the intercept a, this term right here. And so without loss of generality, we can normalize it to something, and 1 turns out to be a convenient normalization. That's no different than estimating cross-sectional time series tests without an explicit risk-free rate in there. We immediately rewrote everything in excess return form, and that's the same I've done here, but we're losing a degree of freedom as a result of it. So to see that a linear stochastic discount factor is equivalent to a linear factor model, you just plug and chug. So you take your stochastic discount factor, plug it into your fundamental pricing equation. That's right here. And then you rewrite it. You get expected excess returns minus beta times the product of expected excess returns and factors. Turns out this is the cross-sectional relationship we're going to test. But then the expected product of two random variables is the covariance plus the product of the expectations. So we can rewrite all of it, and in the end, what we get is a factor model exactly identical to what we had before. We get expected excess returns equal to betas, a time series regression coefficient, multiplied by a lambda coefficient, which in this case depends on the variance and the mean of the factor. So if we can rewrite a model, a linear stochastic discount factor model, as a linear beta pricing model, we can go the reverse, of course, as well. We can start with a linear beta pricing model and reverse engineer what is the implied linear stochastic discount factor model. That means there is another way of testing linear beta pricing models. You start with a Kappa, you say, well, what does it imply for the stochastic discount factor? It implies it's equally linear in the stochastic discount factor form. And then we can test it. And what we would test in a stochastic discount factor version of cross-sectional regressions is simply that the pricing errors on average are 0. So this is our fundamental pricing equation with the linear factor model already substituted in for m, the stochastic discount factor. And we're testing that the average errors are 0 which is the same as testing that the average excess returns are equal to beta times the expected cross product of returns and factors. This is a cross-sectional regression right here. It's the same as the previous cross-sectional regressions, except that what our regressors are now is expected, is these average products of returns and factors, as opposed to betas. Everything else is the same. Now, because things are already set up in moment condition form, it's natural to simply proceed with Gmm estimation. And so standard Gmm techniques are used to estimate the B coefficient, and are used to test whether or not these conditions here hold in population. That's just a standard J-test in Gmm estimation. We're just testing whether the moment's conditions hold. That's the same as testing whether whether the model is true. So Gmm on the stochastic discount factor representation of the model is nothing more than cross-sectional OLS of average return on excess returns, that's a y variable, on the average cross product of returns on factors. And that would typically be your first stage estimate when the identity matrix is your weighting matrix. And then when you use a second stage weighting matrix, if you use in particular the residual covariance matrix, what you end up with is standard GLS regressions. So it's the same as what we had before, just different, slightly different regressors. There's one final variant of this procedure that absolutely requires mentioning here, if for no other reason historical value, and that's Farmer-Macbeth. So Farmer-Macbeth was one of the first variants of cross-sectional regressions, and it actually had a couple of, one particularly important aspect in it that I'll come back to in a second separately. But Farmer-Macbeth is a three-step procedure. The first step in Farmer-Macbeth is to estimate betas from stocks, or in their case actually portfolios of stocks, in a pre-formation period, estimated over some pre-formation period. And so they estimate betas from portfolios and then run cross-sectional regressions the same way that we've done, except rather than running one single cross-sectional regression of the average return on beta, Farmer-Macbeth ran capital T cross-sectional regressions, one for each time period, of the realized returns on beta estimates, and obtained by doing so a whole time series of lambda coefficients and alpha coefficients. You can then test whether or not the alphas, these residuals here, are jointly zero, or whether the lambda, the price of the factor, the premium on the factor, is positive, for example, in the cases of Kappa, by simply constructing tests with simple sample statistics. But we also obtain sampling distributions through the repeated observations of these alphas and lambdas, so we're gaining some information about how are the alphas correlated through time, for example, that we can adjust for when we look at the distribution of these estimates done here. Before I go on and show you some pictures, I want to just point out one important thing that I'll come back to. One critical step, which I have ignored to describe in more detail because I know I'm coming back to it, is that in the very first stage of Farmer-Macbeth, there's a portfolio construction step. And the portfolio construction step in Farmer-Macbeth was such that the portfolios had relatively stable betas, and that there was a large cross-sectional distributions of betas through the use of so-called beta-sorted portfolios. I'll come back to that. But I want you to just keep that in mind before I move on, and of course we'll get back to it in a couple slides. So here are pictures out of Cochrane, which I find enlightening to illustrate how the different approaches of testing linear factor models are different or similar. So this picture basically just shows the outcome of a test. They're all going to look the same with slight variations that I'll point out to you, but let me get the general setup of the picture across, and then we'll go from there. So in this case, we're using size-sorted portfolios on the CRISP universe. On this axis here, we have monthly average returns, ex post. And on this axis over here, we have measured time series betas. And the model, in this case the Kappa, implies a simple linear relationship with a zero intercept, which we've enforced, between average excess returns and betas. And that linear relationship here is that line in the picture. The dots are all of our assets. There's 10 of them in our case. And there's one particularly important asset, which is this one right here. That's the value-weighted return on the market portfolio. That's the factor. So a couple of things to notice in this regression. So what's estimated in this model? Let's start there. What's estimated in this model are these betas. What's fixed in the model is the slope of this line. And that's because we're talking about time series regressions. Because that slope of the slope of this line was identified through one particular point, which is this market portfolio here. And that was the point about the market portfolio as a traded asset. Therefore, we're imposing that restriction to start with. That fixes the line of this slope. And so we estimate the betas, and the differences between the line and the dots are alphas. And we're simply testing whether or not jointly those alphas are zero. This guy up here being our smallest market cap portfolio, the one that's particularly puzzling for the Kappa. So now contrast this to cross-sectional regressions. In a cross-sectional regression, we get the same points still. Those are the average returns. We're getting the same estimates of alphas, because those are coming from the time series regressions. But what we're doing now is we're running a regression of average returns onto the beta, so we're getting a different line. And that line is constructed to minimize as much as possible square deviations of our alphas from our fitted line. So we've added a degree of freedom, which is the slope of this line. We allowed it to vary. That's because in the cross-sectional regressions, in general, the slope of that line is not identified by the factor. And so it becomes a free parameter. We get to fit it. So therefore, we have an extra room to make the model look better. Now, that's only in this context when we use OLS regressions. Actually, what John did here is he used the market portfolio as another traded asset. And he then looked at a GLS estimate. Well, in a GLS estimate, the market portfolio would be fitted exactly. The variance of the residuals would be zero, which forces the regression to go once again through the market portfolio. And so John points out in his book at great length that when you do cross-sectional GLS regressions with your traded factor portfolios as test assets is identical to time series estimation. Because you're forcing your line, or your plane in a multivariate setting, you're forcing your line to go through the factors again. And when you do that, it is no different than when you're running a time series regression. Oh, sorry. And I was going to show you that it's exactly the same line, but maybe that's a moot point. There's your line. There's a third picture. I'm sorry, the computer's a little slow thinking about these pictures. There we go. There's a third picture which shows you these stochastic discount factor cross-sectional regressions. And so everything is identical. The only thing that's now different is that we got expected cross products of returns and factors on this axis here. So we got a first stage OLS, we got a second stage GLS estimate, and everything is in all other regards identical to cross-sectional regressions. So you can look at what are the differences in terms of the test statistics that you obtain, and it turns out they're all very similar between the three approaches in this particular application. So let me not dwell on it too much. So I got a couple of odds and ends on factor models that I thought we should spend just a little time on. So far, we had a kind of a generic alternative hypothesis in mind. Our null was our intercepts are jointly 0. The alphas are jointly 0 either in the time series context or in the cross-sectional context. And the alternative is, the model doesn't hold. And so that's what we've tested. But in many cases in modern empirical work, we actually have more specific alternative hypotheses in mind. And those alternative hypotheses typically come through a preliminary portfolio type of analysis, where the researcher may sort, for example, stocks into portfolios on the basis of stock level characteristics, such as the stock's book-to-market ratio. And in that case, really our hypothesis is a little bit more specific in that the null is still the model holds, but the alternative now is the model doesn't hold, and instead expected returns are somehow related to characteristics, and I've just written out a very linear specification here. There's nothing that says they have to be linear, but you might think that's a good starting point. So the alternative is alphas are in fact related to characteristics. Well, it turns out that that's another advantage of cross-sectional regressions, is we can explicitly test that hypothesis in our cross-sectional setup. We can run a cross-sectional regression of average excess returns on asset I, on the betas that we measure from time series regressions, as well as any firm characteristics you might want to toss in there in order to explicitly test the hypothesis are average returns related to characteristics in a way that is not already consumed or absorbed, accounted for by betas. And so when we think of cross-sectional regressions, we think of them as being necessary in two settings. I mentioned that earlier. I'm not sure I stressed it. One setting is, of course, where the factor is not a traded asset. You have no choice but to use cross-sectional regressions in that context. And the other is where we're interested to see whether perhaps average returns or expected returns are explained by things other than betas. And so in the original Macbeth paper, that firm characteristic here was idiosyncratic risk. Because back then we were still wondering, does the model hold? Is it true that there is no compensation for idiosyncratic risk? And in fact, the answer they found was that's true. The beta explains all variation in average returns, at least along the dimension of idiosyncratic risk in their application. So that's cross-sectional, that's firm characteristics. Now, one could, in principle, do this sort of testing in time series regressions as well, right? So we could estimate time series alphas and then run another second stage regression where we relate those alphas cross-sectionally to characteristics. And that's something that's equally feasible to do. We'd have to think once again about the generator regressor problem. But other than that, there is no reason not to think about characteristics in the time series approach. But this is a more straightforward, immediate way of thinking about characteristics. So I promised I'd get back to portfolios. There's many reasons for why we form portfolios in finance. The two most obvious ones are that stock level regressions are way too noisy. If you think about the signal to noise ratio of a single stock, it's just mostly noise. Volatility of single stock names, can be 60, 70% annualized, and we're trying to extract means that are on the order of 6% to 10%. So a massive signal to noise ratio. So one way of reducing noise, of course, is to form portfolios via diversification. Idiosyncratic risk will go down, and the systematic part, the expected return related part, will start to emerge. The other reason is betas are time varying, most likely. And when betas are time varying, we need to think about more sophisticated ways of estimating those regressions. Whereas if we manage to form portfolios that have constant betas, we can skip that step and think about unconditional moments. So the Macbeth procedure actually solves this problem by forming a very specific set of portfolios, which were beta-sorted portfolios. And the procedure is something like this. Each portfolio formation period, call it annually, the June of every year, you obtain a noisy estimate of firm level betas through rolling regressions looking backward at that point in time. You then sort stocks into beta portfolios on the basis of that historically measured noisy beta, so that you have high beta stocks in high beta portfolios, low beta stocks in low beta portfolios. And you call those beta portfolios, and the basis on which those beta portfolios are constructed are those pre-formation estimated betas, noisy betas from single name time series regressions. But the benefit of this, or the hopeful outcome of this, is that what you end up with is a set of portfolios that are fairly homogeneous in their betas, meaning that all the stocks in the portfolio have roughly the same beta. They should be, because they were formed in such a way. That the beta is relatively constant through time. So if the beta distribution in the cross-section is constant through time, then the beta of beta-sorted portfolios should be constant through time. And that there is a nice spread in the cross-section of portfolios in beta, the regressor. So this brings us back to standard OLS theory. The precision of our slope estimates depends critically on the cross-sectional variance of our regressor. And the more spread in the regressor we get in a scatter plot of x and y, the more precisely can we pin down the slope. And so these beta sort of portfolios are great portfolios to use in a test for betas or regressors, because they are constructed to have maximal spread in betas. Well, somewhere along the way, we forgot about pre-formation betas, and we replaced sorting on factor exposures with sorting on stock characteristics. And most empirical work you see now use portfolios sorted on size and book to market and other characteristics. That is fundamentally bizarre to me. So sorting on characteristics is like sorting on ex ante alphas instead of sorting on your betas. It's like sorting on your residuals or your intercepts, as opposed to sorting on the betas, your regressors, which sorting on the regressors from statistical theory perspective just makes so much more sense. So there's some unintended consequences, of course, of sorting on alphas. One is that when you sort portfolios on alphas, what you might end up with may not at all have constant betas. Let me show you that picture first. I'm sorry. I don't know if it's moving or not. Hold on. Yeah, it did move. So I like this picture from a paper by Andrew Ng, which shows you a rolling sample market beta of value and growth portfolios. Value portfolios are portfolios with low book-to-market ratios. Growth portfolios are portfolios of stock with high book-to-market ratios. These are our standard pharma French test portfolios, and they were formed on the basis of characteristics, not betas. But you would hope that maybe because they're kind of similar stocks always, that somehow their beta exposures are always the same. But it turns out that's not at all the case. That if you look at rolling betas of these portfolios, they can go from 1.2 to 0.8 over the course of a couple of decades. And so we have ended up with portfolios that have highly time-varying betas, that we nevertheless apply techniques with constant betas to. So that's a problem. Characteristic sort of portfolios will not stabilize your beta unless you happen to be lucky and the betas are functions of characteristics. But that seems like something you can test in the first place. Characteristic sort of portfolios may also not generate any cross-sectional variation in the thing you care about, which is the betas, because those are your regressors. And without having cross-sectional variation in regressors, you have no power to identify lambda or test a model. And so the classic example of that point is industry portfolios. What a great grouping of securities that are alike. You form a whole bunch of industry portfolios. Well, it turns out that industry portfolios have a rather small spread in betas from the highest beta to the lowest beta portfolio. So you're running a regression of average returns on betas where you basically just got a ball. And whatever slope you fit through there, you won't be able to get any power to identify the slope. And so before I flip through this, that doesn't make any sense to me. I personally would like to see pre-formation betas return this literature. So I said at the very onset that I'm going to focus on unconditional models. Of course, the world is a conditional one. A conditional model does not necessarily imply an unconditional model. And therefore, one response to us rejecting an unconditional CAP-M, for example, is always that, well, that's because the conditional CAP-M holds, and you tested an unconditional version of it, and so therefore that's not surprising. So in a conditional version of an asset pricing model, the expectation, the slope coefficient, and the risk premium all could potentially be time t subscripted because they depend on information at that point in time. The expectation, obviously, the slope coefficient here, that's really a covariance over variance, which maybe both of those may be varying through time, and that picture on the previous slide shows you a great example of when it does. And then this lambda here, this is a reward for risk from an economic perspective. So as preferences towards risk change, the reward for risk may also change. And so that very naturally might be a time-varying property as well. So this makes the model fundamentally untestable. That's the Hanschen and Richards critique of conditional asset pricing models. Because the problem is the following. If I, as the econometrician, look at this, I now need to specify the functional forms and the information sets relevant for the time variation in these betas and the lambdas. If I reject the model, I can always be critiqued of not having used the appropriate information set for specifying those functional forms for lambdas and betas. And so, as with many of these fundamental critiques, they typically get ignored because there's nothing else to do. So, nevertheless, we have approaches of estimating conditional asset pricing models. And the idea here is that if we cannot reject the model with a reasonable specification, that makes us feel a bit better about possibly the world being described by such a model. Whereas, the other way around, if we reject it, we can always come back to this critique. So there's at least two ways to proceed as far as I can tell in the literature. And they basically revolve around two different ways of statistical modeling. One way of statistical modeling is to model in the time series the underlying latent processes. So the first papers on this were modeling covariances and variances here in Garch specifications. Not exactly the same because the residuals are not, there's not an independent source of noise here that the processes would be driven by returns, but still, an underlying time series model for variances and covariances. Likewise, we could write down a state space representation of the betas, treat them as latent variables, and then try to filter from returns what are those latent variables. We could write down a state space representation for the price of risk. Say the price of risk follows an AI1 process with its own shock and try to estimate such a process. So that's a time series specification of the process, where typically we would have independent shocks, and it makes the econometric problem exponentially more difficult because we now have filtering. We have to learn from data about unobservables. Alternatively, and by far the more popular route pursued in the literature, is we simply say, well, we got some observables that we think might be linked to fundamentals in a way that might link to risk aversion, for example, or might link to levels of risk, for example. And so why don't we start out with simple linear specifications or even nonlinear specifications of betas as linear functions of these variables and of our risk premium as linear functions of these variables. And so what kind of variables are we thinking about? We're thinking about, let's say, the dividend yield of the market portfolio or the slope of the term structure as variables that are tied to business cycles and therefore natural conditioning variables to capture time series variation in our coefficients here. So we can do this in any of our techniques. We could allow the slope coefficients and the market price of risk to vary with exogenous predictors. We can do so in time series regressions. We can do so in cross-sectional regressions. I'm going to do it in the stochastic discount factor form. But again, in any one of these will deliver similar sort of results. So we start out with a stochastic discount factor pricing equation, where the expectation here now is conditional in time t. And the stochastic discount factor is linear again in the factors, except the coefficient, linear coefficient here, is also dependent on time t. Note it's time t. It's measurable at t. It's in the agent's information set when they're making decisions, as opposed to t plus 1. So here, we could start with the assumption that this b coefficient here is a linear function of our macro variables. And then we plug and chug again. So we take this b coefficient, we plug it in here. We take the resulting m expression and we plug it into a pricing equation. And we get another conditional pricing equation. Still has a time t subscript, but now has only unconditional moments, parameters in here. Theta naught and theta 1. That allows us to condition down, meaning take the unconditional expectation of the conditional expectation. Everything that's in here you can take an unconditional expectation of because there's no time t subscripts anymore, other than in the random data. And so we end up with an unconditional model, which looks like this. Now expand the stochastic discount factor, and you notice that what you've done is you've turned a one-factor conditional model into a two-factor unconditional model, where the two factors now are the original factor and the original factor scaled by our conditioning variable. At this point, we are in unconditional factor model world, and everything we've discussed before applies to this problem, meaning we set this up as a GMM problem. We can weight moments and end up with OLS or GLS estimates. Now, if you like this kind of way of thinking, which I do, there's lots of things one can do now. So for example, if I wanted to know whether or not there ought to be a quadratic term up here, that's the same as thinking about factor models with missing factors. Because if I had a quadratic term here, a theta to z squared, then I would have followed the same steps, and I would have ended up with a three-factor model down here, where the third factor would be z squared times f, the factor. So we have automatic test statistics for nonlinearity in our functions, for example. They were just missing factor tests. All right, so where are we? So I think we have 10 minutes for questions before we take a break. If you have techniques to find their sampling distributions under the sampling scheme of the given event study, meaning we try to replicate the clustering that is induced by the events that we're looking at, which will differ from study to study, and come up with just empirical distributions. So the discussion will be somewhat more loose, but I'm hoping to kind of do the same thing as what I did with linear factor models and see if I can put some perspective on techniques to give motivation for where they came from. What sort of boundary are we pushing on in terms of methodology when we're substituting one technique for another? So let's first talk about event studies conceptually, why they exist and the question they ask. So an event study measures the immediate and short-term impact of a certain event on the price of a set of securities. And they really designed historically to answer the question of, does an event matter for the value of a security? And so a classic event study in that line of questioning would be an index addition. A stock is added to the S&P 500 index. It is a completely value, under certain assumption, a completely value-relevant event. And so the question is, does it matter? And so you could run an event study. And the event study would look at the collection of all additions to an index and try to compute statistics, as we'll go through, to answer the question, does this event matter to the value of the firm? And if the event matters to the value of the firm, then we would proceed and figure out, why does it matter to the value of the firm? Now, increasingly, though, event studies are being used, or have been used, to also answer another question, which is somewhat unrelated, actually, of whether or not the information relevant for valuation, that is coming out with this event, gets compounded into prices immediately or with a delay. The first is simply a matter of, does the value of a security, the discount rate applied, or the projection of cash flows of a security, does it relate to an event? That's a contemporaneous question. The second one is a question of market efficiency, really. That asks, is the information processed immediately, or is it being processed with a lag? Post-earnings announcement drift, in my mind, is the classic example of that second line of questioning, of whether or not information gets compounded into prices immediately. So event studies are very popular in a broad set of literatures, the bread and butter in accounting and corporate finance, but also in economics and law. So in economics, for example, if you wanted to understand the role of a given regulation or policy, you might conduct an international event study where you have repeat observations of that same policy change happening across the globe and understanding what that does to certain response variables. Likewise, you could think about in legal cases, trying to understand legal liability, the value of certain things happening to your firm, as seen through an event study. So there's two notions of an event study that actually tie back together into the question of whether or not we're trying to answer this first question, does the event matter? Or the second question, is information impounded into prices immediately, which are short versus long horizon event studies. So in a short horizon event study, by my definition, one examines a relatively short window of time surrounding the event in question. So I'm thinking here days and weeks around a given event. And since even weekly expected returns are small in magnitude relative to the kind of announcement of returns that you would realize in an important revelation of news, we can, in most cases, focus on the actual return surrounding the events and ignore the expected return surrounding events, and importantly also changes in the expected return surrounding events. Because if you have an event that has relevance for the value of a security, in principle it's not clear whether it's relevance for the expected cash flows or relevance for the discount rate. So one has to think very hard. If one were not to focus on a very short horizon of time, one would have to think very hard about the expected return implications as much as just the cash flow value implications. So as a result, the way I see it, there's relatively little controversy in the literature about short horizon event study methodology. It's pretty much a very standard procedure. Everybody follows it. The statistics are very much standard. As I said, we have very little statistical theory because the actual clustering of events, we'll get into that, the actual clustering of events varies so much from study to study that we'd only have some guidance as to how to think about the problem. But the methodology is pretty much standard and uncontroversial. The opposite can be said about long horizon event studies. They're extremely controversial because it is the classic of joint hypothesis problem in this case, where over long horizons, months, quarters, and years, one has to worry a lot about what happens to expected returns over that time frame. And so we get into issues of specifying the expected return model, and that specification being just as important as measuring abnormal returns around the event. So where these long horizon studies come from, they come from the motivation of wanting to use event study technology in order to test whether or not information gets compounded into prices immediately or at some delay. And so there's a tendency to try to extend the event window, such as, for example, in the literature of whether or not IPOs are underpriced. This is a literature that runs event studies with post-event windows that last up to years after the initial release of information. So long horizon event studies are problematic because of the joint hypothesis problem. In order to draw inferences about the abnormal returns around announcements and subsequent to announcements, we first have to rely on an accurate specification of the expected return model, especially when we're dealing with firms that grow very dynamically or with firms that undergo severe changes in something or other. It is not at all unreasonable to expect expected return models to change around the event. And so there's a large controversy about how to think about long horizon event studies and what the right technique is and what one can learn from them. And so what I'm going to do is I'm going to focus on the short horizon event studies. That's not to say I'm only going to focus on the first question of whether or not an event matters, but I'm going to abstract from the type of event studies that would look months and years and quarters and years out after the event. Because that sort of discussion, had I gotten myself drawn into it, would have inevitably led us to talk about linear factor models again. Because linear factor models would have been the normal return model that we'd have to subtract from returns to measure abnormal returns in long horizon event studies. And we would have had to get into discussions like why do factor loadings change around events, for example. And that seemed like it was not the purpose of thinking, of talking about event studies. So the goal then is let's talk a little bit about the basic methodology of event studies. And then I'll talk some more about the bells and whistles that one would attach to event study methodology. And I'll show you a brief example that comes out of Campbell or McKinley. So basic event study methodology is, as I said, uncontroversial and basically just relatively unchanged since these two papers by Ball and Brown and Farmer et al. In the late 1960s. The technology we use today, or the statistics we use today, are unchanged. Our understanding of those statistics has changed, obviously, through time, but the statistics are the same. So an event study has the following 4 components to it. You start out with an economic question. That identifies a certain event that you want to study. And you need to figure out what securities you're going to use in order to study that event. So define the event and select the securities you're going to study. Step number 2 is you need to figure out what would be the normal returns on those securities over that event period if the event was not important. And that has to do with specifying and estimating a reference model. This is where the joint hypothesis enters into the picture, where if I have a wrong model selected in step number 2, my inferences about the importance of the event later on may get biased. Number 3, then, we need to compute some statistics, and particularly in event studies, we compute abnormal return statistics, which are the difference between the returns realized on firms over the event period minus what we would expect from step number 2, those returns to be given a model for expected returns. And then finally, we do some hypothesis testing and interpret our results. So my thinking number 1 and number 4 here is where the real meat is. That's where the economic value is added. And as I said, the methodology by now is so straightforward that I view the rest as being fairly mechanical. It's just a recipe of steps to follow. So here are some common reference models, which actually now, it fits kind of nicely, right, following a discussion of linear factor models. It's a nice follow-up to that. But this is where we would start, having defined an event, having chosen securities to study. We would then have to write down a model that we thought returns followed in the absence of the event being important. And so a couple of options here. There is a constant expected return model where we're just assuming that returns have a return-specific average return, nothing else. A single factor model, which looks very much like the Kappa, except this is stated in raw return form. There's no e's there, no excess returns. And notice the intercept. This is the market model, called the market model. It's just simply taking out the covariation between market returns and asset returns without imposing the asset pricing implication on the intercepts. Because we don't want to confound inferences about the event with inferences about a linear factor model, or the CAPM in this case. So we allow that intercept to be free, whatever it is, without imposing the CAPM restriction. Or, of course, it's multivariate extension, where we have multiple factors, still an intercept in the equation. Now, it turns out the nice thing about focusing on short horizon event studies is that because expected returns of a short horizon of time are relatively small in magnitude, it actually doesn't matter so much which one of these you pick, or some alternatives. And so the general advice then is to keep it as simple as possible, so long as you're focusing on short horizon windows and not longer horizon event studies. So given the model, we now have to write down an estimation scheme for the model. And for that, it helps to look at a timeline of a typical event study. Typically, we might have, in a sample that goes from T0 to T3, let's say that's today, we might have 3 windows identified in an event study. The event happens at date 0. There is a window of time between T1 and T2, which is the main window of interest to the researcher. And what we want to understand is what is the extent to which returns over this time period reflect the news that is being released at date 0. Now that may be a single day, or it may be a couple days before and after, or it may start at date 0 and go for some time period, and that choice is driven by the economic question being studied. But we got parameters, and the parameters are in these models, the alphas and the betas, or the mu here, as well as variance covariance matrices. And those parameters have to be estimated, and generally they're estimated over a pre-announcement estimation window. Now, if you happen to have an event that is it causes such fundamental change to your underlying structure of the firm, you may also use this post-event window to estimate those parameters. So what kind of event would that be? For example, an IPO is a great example. There existed no returns prior to the event, but we want to understand what happens to returns around the event, so one might use post-event information to estimate those parameters. The key is what you don't want to do is contaminate parameter estimation and return inferences over the event period. That's why that's being separated out as a separate timepiece. So the parameters of the reference model are typically estimated over this first time period here, the estimation window, and then held fixed over this event window unless you have some specific information that tells you to do something differently because of the nature of the event. So the recipe then for an event study is very simple. One takes an event at date 0. One estimates the reference model over this estimation window, and then simply records the abnormal returns realized over this event window as the difference between the realized returns and the expected returns given the estimated return model. And that all is captured in abnormal return statistics. So this is an abnormal return of firm I at time tau, where tau here goes from the beginning of my event window to the end of my event window. Those are the returns I'm interested in for each of my firms. It's just the difference between the return on that firm minus the expected return on that firm. Notice the hats here, that's symbolizing the fact that the reference model had to be estimated in the estimation window previous to the recording of abnormal returns. In order to draw inferences about the magnitude of this abnormal return, we would want to know what is the variance so that we can form a standard t statistic or z statistic, depending on whether we're happiest to assume normality as well. And so the way to do that is you assume iodinous. And if you assume iodinous, you can write the variance of the abnormal return as the variance of the epsilons plus the variance induced by the estimation error in the reference model. The variance that comes from the alpha hat and the beta hat, as opposed to the variance that comes from the epsilon in population. Now, it turns out that second piece is actually quite nasty if you think about it. Because what it does is it creates persistence as well as cross-autocorrelation in abnormal returns, even in the absence of underlying persistence and cross-correlations in the epsilon, or under the assumption that the true returns are IID. They're very simple. If I misestimate my betas on all my firms, then I would systematically also misestimate the epsilons relative to the population values. And that introduces an extra error term in precision in the contemporaneous estimate. But it actually is the same error that I would induce estimate after estimate, return after return, thereby inducing persistence in the residuals. This is an issue when the event window becomes short. The estimation window becomes short. So let's go back to the timeline. If this period here is too short, my estimates will become too noisy, and my estimation error term in the abnormal return statistics, the term that is being accounted for here, starts becoming relatively large. And so the resulting prescription to resolve this issue is to use sufficiently long estimation periods. You can think of this term here as guiding your choice of how long the estimation period has to be, given that you'd want to proceed most likely by assuming that this term can be ignored. And I'm going to do that going forward. Because already, even without any further clustering, this would already make inferences much harder once we start doing what we're going to do next, which is aggregate abnormal returns across time and across firms. So we're going to assume that those are 0 and that the only error in these abnormal return statistics is coming from the epsilons. So now, what we want to do is we want to draw inferences about the relevance of the event for the value of the security. But if you look at just a single abnormal return on one stock, that quantity is still extremely noisy as a way to draw inferences about one event. So what we do is we aggregate observations in the time series as well as in the cross-section. So in the cross-section, the way we aggregate information is we simply take an average over n firms, each realizing the same event. But we do so by lining up our observations in event time. So if firm 1 is realizing its event on the 1st of January and firm 2 is realizing its event on the 15th of January, we add the return on the 1st of January for one firm to the return on the 15th of January for the second. Essentially what we're doing is we're shifting the observations for the various firms to line them up such that they all have the same date 0. This is the critical part that destroys most of our ability to come up with reasonable statistical theory underlying these abnormal return statistics, which is that we don't know ex ante how we're going to be shifting those observations around. And if there's any correlation that exists between returns and the cross-section, we will be inducing correlation terms in the variances and variances of these abnormal return statistics. We'll come back to that in just a little while. So in the first step, we can aggregate abnormal returns cross-sectionally across firms. And then in the second step, we aggregate abnormal returns through time, either at the individual security level, where we start at the beginning of the event window and go to the end of the event window, summing up the returns, coming up with a cumulative abnormal return over the event window, or at the aggregated, cross-sectionally already aggregated form, where we take the cross-sectional average abnormal return tau days into the event period and sum them up and come up with a cumulative average abnormal return. So going back to our event window, we've aggregated returns from this time point to that time point. Why would we want to time aggregate returns? Lots of different reasons. You might think that there is a time delay in the way information gets processed over a very short period of time, 1, 2, 3 days. You might think that there's some microstructure issues that cause the information that is already impounded into true prices to not be revealed yet in observable prices. Or you might just want to average out some noise because you know that there's a lot of noise in daily returns, so you rely on some time series averaging argument to get rid of that. Now it comes to hypothesis testing. And what we want to study is whether or not the abnormal return from this event, or the cumulative abnormal return at the stock level over some horizon, or the average cumulative abnormal return of all firms over some horizon, are 0 or positive or negative, depending on which way we think the event affects the value of the firm. In order to do that hypothesis testing, we need a variance expression for those statistics. The easiest one to calculate a variance for with the least offensive of statistical assumptions would be this cumulative absolute average residual at the stock level. So the stock level residuals, if we assume that they are IID through time, so these epsilon i's here for firm I by itself, if they are IID, then the variance of the sum of returns over some L observations is just L times the variance of the individual epsilons. So that's easy enough, and as I said, not so offensive in terms of assumptions to make. The other two expressions, the average abnormal return across firms once we line firms up in event time, and particularly the cumulative average return across firms once we line up firms in event time, become a lot more complicated because they depend fundamentally on the cross-sectional correlation of event returns, which itself depends fundamentally on the clustering of events. So consider two examples. One example, you have events that are completely non-overlapping, so that none of the event windows overlap. In that case, it's fair to treat each of the cumulative abnormal returns, stock by stock, as independent of one another. That will be fairly simple to deal with. Take the other, where all of the where each of the events are all happening at the same time. A legislative change that affects a whole bunch of firms all at once. Now you you would think it's very reasonable that there's very strong correlation in the in the abnormal returns across stocks, and this statistic needs to adjust for that correlation. When you mix those two extremes and go to the intermediate case, it gets even more complicated. Because now all of a sudden, when you have event windows that are not perfectly lined up, but also not perfectly separate, you start introducing lead-lag cross-correlations. And those lead-lag cross-correlations show up in the variance term for this cumulative average abnormal return statistic. So we can proceed by ignoring those issues and pretend or assume or check that our event windows are in fact non-overlapping. Then we can treat the abnormal returns and the cumulative abnormal return stock by stock as being independent and come up with the variance of our abnormal return aggregated in the cross-section is just 1 over n squared, the variance at each individual guys. And so just the average there. And the variance of our cumulative abnormal returns, again, you just aggregate up all the variances from the individual pieces. So that's easy enough. So here's a picture of a typical event study. This is taken at Campbell McKinley, and it is a picture of an earnings announcement event study, classic event study. And I like this picture because it illustrates a lot of different things that happen in event studies that are worthwhile to keep an eye on and to discuss. So first of all, let's discuss the setup of the study. These are earnings announcements at the firm level. They typically happen 4 times a year per firm. Date 0 is the release of the information. And we're looking here at a 2-month event window that starts minus 21 days before the event and goes to plus 21 days after the event. So there's, you want to think of a hypothetical line right here that goes right there at 0 where you see that massive returns. That's when the news comes out. We're plotting cumulative abnormal returns. That's what I had denoted as my AR bars. And we're doing it actually for 3 sets of firms. We're doing it for firms that have no news. We're doing it for firms that have positive news. And we're doing it for firms that have negative news. And what we're trying to study here is whether or not this news has relevance for the firm. And it is very clear that there is a contemporaneous, very large reaction of these cumulative abnormal returns to the piece of news, which if this return right here is statistically significant, or maybe the absolute value of these 2 returns here, that would give us evidence to conclude that, that this event is meaningful economically. But there's more going on in this study. So the one thing that's going on here that we haven't really discussed, but you can see it here, is the segregation of abnormal returns by type of news. So we can test whether bad news is different from good news. And it's very clear we don't need a statistical test in this case, that it would be. But otherwise, one could devise a statistical test that compares the average abnormal return in this group to the average abnormal return in that group, standard difference in mean tests. There is some abnormal returns going on before the event that's worthwhile to point out. This is sample selection. Remember that we were selecting these samples already on the basis of whether or not they had good news or whether or not they had bad news. So to the extent that good news firms also have good things happening to them before the event, and bad news firms also have bad things happen to them before the event, this is not at all surprising. And it is not a violation of, it's not necessarily evidence that something has happened here or that information is leaked. It's just simply it's a sample selection issue. There's also some action here after the event, which people in the accounting literature have coined post-earnings announcement drift, which actually this is not post-earnings announcement if this looks more like a reversal right here. But it just suggests that there's a large return, and then there is a subsequent move in cumulative abnormal returns that, if it was statistically significant, would suggest that this initial move was perhaps an overreaction, leading to some conclusion of potential inefficiencies. Now you might suggest that there is an inefficiency here. And then the typical post-earnings announcement drift type of paper would have this event window here going out to the next quarter, all the way out to 1 year. And what we would actually see in those studies is a gradual increase in the cumulative abnormal returns with jumps happening at the subsequent quarterly announcements, if you really control for those carefully. So that's an example of an event study, the kind of study that we have in mind. Again, the statistical inferences here are about the magnitude of these jumps. Are they sufficiently large given the sampling distribution of these cumulative abnormal returns here? And perhaps about the differences between this group of the population and this group of the population. And then finally, see what happens after the event in order to draw conclusions about the immediacy with which information gets impounded into prices. So that's the basic event study setup. But there's lots of bells and whistles that people have talked about as they have over time documented and discussed the various shortcomings of this procedure, which are worthwhile reviewing and at least touching on. So the first is dependence, and this is really the biggest one of them all, and that is that if event windows overlap, then abnormal returns are correlated either contemporaneously if two firms happen to have abnormal returns on the same date, perhaps, or at a lag. And the lag structure is particularly tricky because it depends on the overlapping nature of the events. So if an event if event windows overlap by 1 day, or don't perfectly overlap by 1 day, let's say they're offset by 1 day, it's a lead lag correlation at day 1 offset. If they're 10 days apart, it's lead lag correlation at 10-day offset and so forth. That depends on the actual sampling procedure. So the common approach to this problem is what Brown and Warner first called the crude adjustment method, which I think of as portfolio construction. So two things this Brown and Warner paper did, which is quite influential in event study literature. It talked about first talked about the portfolio construction technique, and it secondly laid out the framework that basically everybody still follows in terms of the procedure by which you evaluate the quality of your inferences through your resampling procedures. So they discussed the use of resampling of the data, bootstrapping essentially, to obtain finite sample distributions of statistics that have correlations embedded in them through whatever the event-specific correlation structure and clustering is that's induced by that event. So here's what you do in a portfolio construction technique. You form a portfolio of firms that are experiencing the same event lined up in event time, but you do it short periods at a time. So you say, for example, over this quarter, there are 20 firms that experience a given event. I'm going to take only those 20 firms over that quarter, and I'm lining them up in event time. And I treat them as a portfolio, a common observation. I then keep that portfolio constant at whatever offset I've had to move it to in order to line up event dates, and look at it in calendar time going backward to measure its variance. From your perspective, it goes this way, backward, to measure its variance. And what that does is it measures the variance of the abnormal returns, taking into account the lead lag correlations that are induced by having these time scales shifted in a way so that the time zeros all match up, the event dates all match up. You do it over short windows of time, meaning you don't aggregate the whole population like this, because that way you can still account for changing betas in the historical data. You don't have to think that every firm has a constant beta forever. So you do it 1 quarter at a time, accumulate form a portfolio of all the event firms, look at the abnormal return of this portfolio, and normalize, draw inferences with the standard deviation of the abnormal return of that portfolio lined up the way it is lined up in event time, looking back over some estimation window. So that's a very intuitive, I find, way of thinking about how to, application by application specifically, deal with the fact that clustering induces cross-autocorrelations in event returns. There's also heteroscedasticity to deal with, and in event studies, heteroscedasticity comes in 2 flavors. There is cross-sectional differences in the volatility of the abnormal returns. Clearly, there are firms that are more volatile than others. And there are event-driven changes in the volatility of the abnormal returns. So let's first talk about the first one. Cross-sectional differences in the volatility of the returns are accounted for in 2 ways. One way is you might think about a GLS approach, where you take the abnormal return from firm I and you first standardize it by its own residual variance so that it has an equal contribution in terms of units of variance to the cumulative abnormal return. That's GLS versus OLS in an event study environment. The second way that we account for that form of heteroscedasticity already, I didn't mention it, is right here. Right here, when we take the average over the individual asset-specific variances. So we're not just saying, well, this is 1 over n squared times some common variance, but we're actually allowing each asset to have its individual asset-specific residual variance. So that's fairly easy to account for, and it's common practice to standardize the abnormal returns by residual variances before you start aggregating them. The second is a little bit more tricky to deal with, and that is event-driven changes in the volatility of the residuals. This is a very logical one to worry about if you think about it. There is a big event that just happens. Earnings come out. That's very important for the valuation for this firm. It's reasonable to assume that the variance of this firm's return is also higher when that event happens. And so, or around the time the event comes out. So in order to address this, that's a little trickier, and it's addressed by this Bermudal paper. The way you can deal with this is you estimate the variance of the abnormal returns cross-sectionally as opposed to from the time series. Because you have to get a sense for what is the variance of abnormal returns over event windows, not over estimation windows that don't have events in them. And so rather than forming a time series estimate of these abnormal returns, you would form a cross-sectional estimate of these abnormal returns under assumptions of independence. And then there's one final thought I have on event studies, which is, typically you see event studies being formulated in this classical event study methodology, abnormal returns, cumulative abnormal returns, and so forth, which then makes you have to think about how to deal with particularly a dependent structure in the data. But there is nothing wrong, and in fact it seems very intuitive to me, to actually run an event study in a multivariate regression framework. And this has now become fairly standard in the accounting world. This was first introduced by a paper by Rex Thompson and Catherine Schipper, where basically you have a whole bunch of time series regressions. You got individual regression coefficients, which you would have had to estimate anyway, because that would have been your reference model. But now, together with estimating the reference model, we also get to estimate the event returns, which are dummy variables, or coefficients on dummy variables. And the dummy variable, very simply, is equal to 1 if firm I had an event on this particular date, t minus tau. Okay, so why t minus tau? Well, if I just had a dummy variable for my actual event date, I would be able to test whether or not there's an abnormal return on the day of the event. But general event study methodology actually puts a window around the event and asks whether the cumulative return over that event period is 0. Well, I can accomplish the same here by having a sequence of dummy variables that turn on. One dummy variable that turns on 3 days before the event, one dummy variable 2 days before the event, all the way until 3 days after the event, giving me a 7-day event window now through 7 dummy variables. I would get 7 different of these gamma coefficients, which I may restrict to be the same in the cross-section or not. I have some flexibility there. And basically what has just happened is I've replaced inferences drawn about the abnormal return of firm I at time tau with inferences drawn about these regression coefficients gamma I drawn at time tau. But because these regressions are still all lined up in event time, in calendar time, I don't have that cross-correlation issue to deal with anymore. I now replace it, however, with a more complicated waltz type of testing situation where I got to jointly test that the gammas or some linear combinations of these gammas is 0. So that makes the testing a little bit more tricky. But in principle, the inferences become cleaner because I don't deal with these ad hoc constructed test statistics, which are the cumulative returns that we talked about already. All right, so I'm afraid that is all of my insight that I have on event studies. Now, I should mention that what I did is I compiled a, before we get to questions, I compiled a reading list, which is not part of your slides.